Hi, welcome to another lecture on business mathematics. Today we are going to have another installment on our series on powers, parentheses, polynomials, and optimal boxes. So this is going to be part 3 of the series. So you remember that we talked about powers, x squared, x cubed, and so on. Then we talked about order of operation and the role of parentheses there. And when we combine all of these things, we get polynomials. So polynomials are the powers of x multiplied by some numbers and added and subtracted. Now comes a very pleasant surprise that this little bit of math that we learned here is crucial in designing optimal box. So what was the story of optimal box? We said that you can have a cardboard in a rectangular shape. We could go ahead and cut corners in the shape of a square and then fold this cardboard until it makes a box. Now this box has a certain volume, and a typical design consideration is to make this volume to be the maximum it can be. So obviously if we make our square very small here, the box is going to be very shallow and the volume of it will be very small. If you make this square very big, then essentially what you get is like folding a cardboard, and what you get again is a very little volume. So somewhere in between there is this sweet spot where the volume becomes maximum. Last time we showed a little demo of this thing, but let's start this time with that at the beginning, see what is meant by our design consideration. Okay, let's go ahead, take a look at this problem in a demo to see what is meant by all of this. So here is a page from GeoGebra, a very nice website where teachers put their work, and you can actually use it and write program yourself to demo various aspects of mathematics. So here we have a cardboard, sheet of cardboard. You decide on the length and the width of it, and here you decide how much to cut from each corner. So suppose I want to cut 2 squares. So here's one, here is, say, 2 squares is being cut from the 4 corners, meaning square of size 2 I meant. Let me correct myself. So here on this picture you see that this is being cut. Now we are going to fold it on the dotted line. It gradually makes the dotted line, so as you move this thing, first it makes the dotted line, indicates for you the dotted line, then it starts to fold it. Okay, so here's the folding, the flaps. Once the folding is completed, it shows the whole box to you in green color. So here is your box, and then we put the flaps back and we have such a box. Okay, now the issue is the following. If I had started with a smaller, let me go back to the beginning. Okay, so if I have cut a small square, then when I fold this, so let's do this thing quickly, it gives you a different box, and therefore it's going to be a different volume. Well, the question is, among all these boxes, which one of them has the biggest volume? Well, that's a standard thing in business, that when you are running an operation, you have certain constraints on your resources, and you want to combine all these resources into perhaps maximizing your profit. So that's called optimal design. The best design for your situation would be certain uses of all your resources so that something becomes the maximum it can be. So for a company, typically a profit or something like that. And here is a simple mathematical version of that. So We don't have an elaborate business here. We're just making a box, and our objective is to make the volume to be the largest it can be. Okay, what does this issue have to do with polynomials? Let's go back and let's get started on this problem. So we learned about all stuff with the polynomials, and now next level is putting all of this thing into some good use and see what can we do with it. So for starters, let's suppose we have some sheet of cardboard with a certain dimension. Let me say this is like 8 inches and perhaps this is 15 inches or something like that. So two numbers are given to us for the dimensions of our cardboard. Then we go ahead and decide to cut certain squares. As I mentioned last time, in practice they don't completely cut the squares, rather they cut one side of it, so that when you actually fold the flaps you can staple those squares and make a somewhat usable box. At any rate, that's a practical consideration. Doesn't have to do with anything to do with our mathematics, but what we are going to do is to fold this along these dotted lines. We are going to assume that the size of the square that we are cutting is x. So all of these things are, of course, same dimension x. All of our boxes have to be, all of the squares have to be same, so that the box is not lopsided or anything. So once you take this thing and, when you fold it, what would be the dimensions? Well, let's go talk about that. The dimension, like what is this? What would, let's say it's here. It evaporates. So my cardboard originally was 8 inches wide. Then I'm cutting 1x from one side, 1x from the other side. So this is going to be 8 minus 2x. How about this other one? Let's color it differently. So these two sides, what's that going to be? Well, the overall was 15, and then you cut x from either side, so this became 15 minus 2x. And of course, this one is also 8 minus 2x. Then what? Then when you bend you fold the flaps, that x becomes vertical here. It becomes the rising side of the box. So that is of size x. Let me. So something like boxes, maybe you get it from a post office box that a little bit sturdier than this one, a slightly different design, but here it is. So we said our design objective is to maximize the volume. Well, first of all, what's the volume of a box? Let's show it by V. This volume, we said it depends on how much you decided to cut. So we learned about the functions V of x. So volume, when the square that is cut, when square is of side or size x. So V of x means that, not V times x, V of x. Well, what's the volume of any box? If I have any kind of a box, I take the length and width and height, or however you want to call it, and the volume is the product of these three dimensions. So maybe I write my x first. That's the height of it. Then the blue dimension is 8 minus 2x, and the yellow dimension is 15 minus 2x. So we multiplied the three dimensions of this box. Each dimension depended on x because we have to decide how much we want to cut. So what are we getting now? We are getting product of three terms. When I multiply this thing out, I'm going to get a polynomial. So that's why we were studying polynomials. I'll have a polynomial. So let's just practice multiplication. You could just leave it. This is as it is. It's pretty good by itself. It's very useful to write it like that. It's a factored form. If you want to multiply it, I go ahead and multiply these two first. So leave the x out for a second. 8 times 15. Let's write everything I'm going to multiply, and then we multiply later. Minus 8 times 2x. So I hope my x's and multiplication signs don't mix up. And then I have another minus 15 times 2x. And then I have 2x times 2x, which is plus 4x squared. Is that right? Minus times minus is plus. 2 times 2 is 4, and x times x squared. So x, that is 120. I have this is 16, this is 30, the total of what's that, 46x, and then I have a 4x squared. I still have an x on the outside. I can multiply that through as well. 120x minus 46x squared plus 4x cubed. So sometimes people like to write from the highest exponent and go down from there. It's all the same. Sorry. Sorry for that. I lost my screen for a second. So this is we said we want to write it from the higher power to lower power. Either way is fine. So what did we get at the end of this thing? We have volume as a function of x, and that is 4x cubed minus 46x squared plus 120x. This is the same as what we had at the beginning. This was the factorization of this thing. That's also nice to have. 8 minus 2x, and then 15 minus 2x. So remember, we had a design consideration. What size to cut? Size, we take it to be x. We worked out the volume. Whatever x do you decide, this would be the volume. Now, next big question is, what x is the best x? That's the optimal design. Well, looking at this, what's the range of my x anyway? X starts from 0 and works its way. Of course, I cannot cut more than halfway through this. Of course, if I cut that big of a square, not much of anything is left. When I fold it, this will look like a folded page. It wouldn't have any volume or anything to it. But we can see that our operation makes sense. X has to start at somewhere between 0, and it doesn't make sense to go past 4, because then one square is going to interfere with the other square. 15 is big enough for us to go as far as 4, but the other side, 8, limits our x between 0 and 4. Okay, so far with me. Next question is, what is the best x? Okay, as we go toward the end of the semester, we are going to bring some big guns into this fight, and we are going to learn about differentiation or derivatives, and that's going to help us answer that question. That is the topic from calculus really. But right now our tools are limited. Our tools are limited to, well, graph the function and see what's the highest point of it, and let's work it out like that. So let's go ahead. We want to graph this. I'm going to use a graphing calculator, and you might as well also learn how to use it. One of the best ones that is out there is called Desmos, so we are going to go ahead and try to find that. Okay, so this is the desmos.com/calculator. You can graph your function here quickly, and we can be done with that. So over there we had called it V for the volume. It's traditional to use letters Y and X, so I'm going to use the letter Y here. Y is equal to X times, and then we had 8 minus 2X, and then I had 15 minus 2X. I can write it like that, or if I want, I can write it the way I had multiplied them out. It was 4x cubed, minus, what was it, 46x squared. I forgot what I had, let me go back. 46x squared plus 120x Notice that the first graph was red. It got covered with the blue one. If you click on this thing, you take that one off the page. If you click on it, it comes back. If you want to take that thing off and you want to bring it and take the other one out, so either of them is fine. Now we notice a problem here that our graph is exceeding the page, is going all the way up, is getting, it's being chopped off, and we want, well, we don't want it to be chopped off. So I have to go adjust my screen, just like what you do when you are taking a picture and you want to frame your subject so that you're not chopping off their heads or feet or something. And the way we control this thing with this wrench. This range, here we notice that we are cutting the top and bottom of this thing. So I go ahead, start lower, like minus, say 20, and go as high as 20. So this, my axis went as high as 20, but still not good. Still the heads are being chopped off. So I go 40, still chopped off, you see. Let me take this thing off, you see. It's still chopped off. We want to have the whole picture. So let's go for the kill and just go to minus 100 and 100. Now we see a nice curve. So my axis on vertical axis went as far as 100. My horizontal goes up as far as 10. You can of course pan this thing left and right if you wish, and all sorts of other things. So this is the graph of that function. Is that right? The volume, or over there was v of x, here is y of x. This is a graph of the function. What is it that we want? We want the highest point on the graph. You might say, well, here is very high, and just go pick that one up. But you remember we said that x is not totally free to be anything you want. First of all, it can't be negative. It doesn't make sense to have a negative square cut off. And on the other hand, you cannot cut more than half this side anyway. So your x has to be limited to 4. You can't go past that. That doesn't make sense to make this square to be on top of the other square. So when we go here, we want to reflect the same fact. So suppose you want to cut a picture so that it's not all over the place. I want to limit my x's. What do I want to limit as? I want to start at 0. X can be anything larger than that, but also has to be less than 4. So I put it, so in the curly bracket, I put domain that I want. This is what your textbook calls the practical domain. Like a math function doesn't care what x is, but in practice when you are making boxes, your x only makes sense if it is between 0 and 4. So this is the practical design that you face. So what is it that we want? We want this is our volume. This y is our volume. We want it to be the biggest it can be. Biggest means, well, highest point on the curve. The software by itself, it just pinpoints high and low and intersections and so on. So at this highest point, we have a x coordinate and a y coordinate. What does that mean? This is my screen gets so you see that number 1.666, etc. That's your x coordinate. Your y coordinate is 90.74, etc. So x coordinate, the best x that you can have is 1.666, etc. And then y comes out of that. So in this problem, for this particular size of the paper, the sheet of cardboard that we have, best x for us, best x, it turned out to be 1.666, etc. Which, if you look at it a little bit, you see that is really 5/3. It doesn't have to be always such a nice number, but well, in this case I designed the problem so that out comes a nice number, 5/3. So that's the best x. That's the best you can do. And then, well, putting 5/3 in this is going to be, if you are doing it by hand, and I think might be a little bit hard, but putting it here is relatively easy. The best volume we get, my x is 5/3, then 8 minus 2 times 5/3, and then times 15 minus 2 times 5/3 again. So I simplify, this becomes 5/3. I take a common denominator here, 3. 3 times 8 is 24, and I have to subtract 10. Here I take common denominator 3. 3 times 15 is 45. 2 times 5 again is 10. So it became 5/3 times 14/3 times, what's that? 35/3. And 3 times 3 times 3 is, of course, 27. And 5 times 14 times 35. So you find that with your calculator. So 5 times 14, 70 times 35 is 2450. 2450. Now if you want to get to so many decimal places, I divide it by 27. I get 90.74, and this becomes 90.740, and repeats like that, 740 and so on. So this is a repetition of that. And let's go and see if our hand calculation is right. You see here also second axis 90.74074. Of course, this is decimal approximation. It doesn't show all the digits, but here we actually managed to get all the digits. So the best volume, best x, so the maximum volume is 2450 over 27, which is 90. If you want to approximate to one decimal place, for example, you say 90.7. So that's how many cubic inches of stuff you can put in that box. That's the best you can do. So this is our optimal design. So we had a design consideration, which was what's the maximum volume we can get out of this thing. And then we used our knowledge of volume of a box, length times width times height. We made a polynomial using the letter x for the size of the square we cut. We got this polynomial, turned out to be a cubic polynomial. What is the highest of it? Right now, the highest point of it, we got it by graphing here. We get the highest point. Later on in the semester, we are going to have a much more advanced way of doing this thing. Which is how do you find that maximum point yourself without use of a graphing calculator? How does that going to be done? We said that that's going to be the concept of. So next, toward the end of semester, we are going to come back to this thing, perhaps do a part 4 of this thing, finding answer using derivatives. So I just give a quick preview of this thing, and then we are going to come back to this thing later on. So that we have a picture there, some kind of a function that perhaps looks like this. Well, that function looks like a mountain or something. If you are at some point in this mountain and you are climbing, depending on how steep it is, you are going to struggle more, and that steepness can be measured. That steepness, how steep this line is, how you are climbing, is decided by how steep this tangent line is. That is exactly what derivative is. So derivative is equal to slope of tangent line. So derivative of a function. Suppose this is my point x, some point I am in. Derivative of a function at x is the slope of tangent line to graph of the function at that same point. So if this is the graph of, if whatever I have here is some graph of some function y is equal to f of x, if I choose a certain point and ask what is the derivative there, what I'm really after is finding a slope at that point. Okay, what does this have to do with designing optimal boxes? How is that relevant here? Very simple. When you have a curve like this, what is your slope? Your slope here, slope is positive. Okay, you're going up. How about here? Here slope is negative. As we go from left to right. How about at this highest point? Remember, optimal means the highest point. What happens at the highest point? Well, you're going from going up to going down. At that very top, your tangent line becomes horizontal. And what is the slope there? Slope is between positive and negative. Slope is 0. So our game later on will be to find a slope, set it equal to 0. How do we find a slope? We are going to give certain very simple rules that given your polynomial, you can differentiate it, take the derivative of it, set it equal to 0, and find out at what point you are turning around. So this was all a preview of what we are going to do later on. Our lecture now is going to be connected to other topics that we are going to cover at some point in the future. So until then, good luck and God bless.